Good evening, Dr. Vera.
Good evening, Mr. Jones. Uh, Let me try to send the link to the groups so that maybe if there is several students would like to join, so get somehow accommodate them.
Sure. I got it.
Yeah, so we will wait in about 5 minutes before we start the discussion.
Sure.
All right. Yep. Yeah. So yeah, good evening again, everyone. So thank you very much for joining. This is our third meeting. In the first meetings, I've been discussing about how advanced optimization technique was mostly considered about uh, how to deal with optimizations type of problems where you have limited resources. You want to make decisions that towards some optimized decision function, such as maybe you want to maximize the profit or minimize the operation time efficiency. But instead of using tools that you have been studying in the previous class on advanced optimization technique 1, which is discuss about how to model those problems into its mathematical formulations and assume everything is so-called deterministics, or everything has like a certain value that you can use as a base, right? But mostly problems in real case or real situations was not like that. It was more complex. Most often it involves uncertainty. And those uncertainty factors, we model it as um, a probability. So when you deal with probability, you will start talking about probabilistic model. Yeah. For solving probabilistic model, of course, there are several approaches, such as one of them is simulations. And therefore, we are trying to approach the advanced optimization technique 2 in the setup of um, system modeling and simulation. Okay, so after the discussions, after those being set up, then we discuss about there are several types of simulations, agent-based simulations, discrete event simulation, discrete time simulations, and what are the difference between those. That was part of the slides that we have in module 1. So therefore, in that case means that you are going to dig deeper on which part of the simulations. And in module 1 as well, the slides that in the module 1 we discuss about, we are going to dig deep on more of simulations that is so-called discrete event simulation. So the things that you simulate is based or triggered by change of an event. Okay. Therefore, all the vocabulary, all the setup was towards to when there is a change in the event, what would be what kind of a situations that you can simulate. We have a discussion about the queuing system, where the event would be customer arriving to the system and then enter the system, such as like queuing system like here, customer arriving, and then they need to be served by a server here. And then when customer arrive, yeah, this is a new event, right? And then if there is some customer that already or still in the processed here by the server. So the new customers that is joining here need to be what? Need to be queue here. Right? So they enter the queue. And as soon as this customer was finished served by the server, then the customer that in the queue will replace the customer. Yeah, those are the events that being simulated in discrete event simulations. It's pretty much different with the discrete time simulation where you have continuous observations with the change of time. For example, if you have a time period of observation of 1 minute, so every 1 minute you capture the system and then you see what happened. It may not changing, but because you want to see it in every time interval, then you capture it on each of those time intervals. Therefore, this type of simulations, there is no good or bad. So it's just which one suitable for your needs. Okay. So if you are simulating such as queuing system, inventory system, networks design, and electric circuit system, that would be better simulated in um, discrete event. But if you are want to observe, like said, let's say, a flow of a fluid in some system, then you cannot use discrete event because the flow of a fluid will be continuously updated, right? So something like that. And collision of a car, right? So each time when you need to simulate the collision, so each time the state of the impact would be different. There you need to have like so-called discrete time simulation. Okay. Agent-based is another type of simulation, but I will not discuss it in this class. So therefore, we will put that for further elaborations if you need it. Then meeting 2, which is yesterday, we have discussed about, okay, we're dealing with the discrete event simulations. Therefore, we try to explore what are tools available for discrete time simulation. Discrete event simulations. And one of them is that, hey, we can say that you are not actually need a sophisticated tools to do those discrete event simulations. The things that you need to understood is what is the input for the systems that you are going to simulate? What is the nature of the input on what kind, let's say for a queuing system, we just introduced to input such as, okay, when a customer arrives, there are uncertainty in the time between arrival, right? So those are called inter-arrival time. It is uncertain. Therefore, you just need to capture those behavior, inter-arrival time, and then the time that the customer being served by the server. You can assume it's a like a static value, let's say 2 minutes, on average 2 minutes, you will always simulate. That's possible, but most of the time it would be, in a real case situation, it would be uncertain as well, right? If the things that being handled is complex, then the service time would be different from one customer to another. And those can be simulated easily using spreadsheet. Okay, we are studying about how to create an event list, input of the simulations that would be in the simulation table, and then finally what kind of variables you want to observe. For a queuing system, maybe things such as the queue length, the waiting time, the time that the customer in the system was something that is interested to be observed about. Okay, so what is the input? What are the process and what are the output? Create simulation table. That was the one that we studying in the second meeting. Okay. Now we are going to understood further the things that become the main ingredients of simulations, which was like the uncertainty. Okay. In simulating uncertainty, well, actually, if you want to understood the system better, you need to understood as well how those uncertain factors can be the input, uh, can be the processing time, for example. How does those uncertainty works, or the characters of those uncertainty? Therefore, one of the tools that you can use to model uncertainty events is statistical models. That was what we are going to discuss in this chapter. Okay, so this is a top. No, it's even borrowed from this chapter in the book. So I do give you the reference for this book. So please go ahead if you want to look in a further details. Okay. So as I mentioned earlier, so things that you will discuss, is that real world system. When you want to model a real world system, usually you will face some things that probabilistics. Either it's probabilistics or rather than the things that is deterministic. Like even like let's say what travel distance. Sometimes we always assume, okay, from the flight time from Jakarta to Manila, maybe on average is 1.5 hours. I don't know how many hours. 1.5, 2 hours maybe. But that's when you assume it's a fixed number, then that was deterministic. But in reality, it's not always like that, because 1 hour or 2 hours can be in between. It depends on the situations of the travel. If there is main turbulence, then it will increase. If the path, the sky path is so clear, then you may arrive earlier, right? So there is statistical variations that you can model. You can use statistical model to describe this variation. That's the main idea of statistical modeling in simulations. Okay. Now, the question is how to find an appropriate model. Okay. An appropriate model that represents the phenomenon of interest. Okay. For example, if you are going to understood the appropriate model for inter-arrival time of a customer in the bank, then you need to take samples, right? It's data samples, okay? And then you can, after get the data, you can select a known distributions through educated guess, and then make the estimate of the parameter for those uncertain factors that you are going to model in your simulations. And then finally, even if you want to go further, you need to take the test of goodness fit. Means that how fit the data that you are taking as a sample with the distributions statistic models that you choose. Okay. For example, normally in inter-arrival times of a customer, we will model it as an exponential distributions with the value of the parameter would be some numbers that represent differently case to case. Okay. So that was one of the examples. And this chapter, we will also discuss about several probability distributions. Okay, so several statistical probability distributions and typical applications of those statistical models. Okay. Now, terminology and concepts. Okay. So before we discuss about specific distributions, there is some things that I want to review a little bit. this should be done in the class related to statistics. I hate statistics. I mean, like, I'm not really good in statistics, but we cannot do so much about it because it was everywhere, especially if you're modeling about uncertainty. Okay, so therefore we need to go back to review several concepts such as what are so-called discrete random variables. Okay, so the things that you are going to model, right? Inter-arrival time, service time, demand, what consumption rate. Those are random variables, but there are several types of random variables. At least the most common differentiation is that we do have discrete random variable, we do have continuous random variable. What are those? We will discuss it in the next slides. And then we do also have so-called cumulative distribution function. So basically, these random variables will be modeled in their distribution functions. Okay, and then what are so-called expectation value? Okay, so basically this is also related to this. Okay, first of all, discrete random variable, what are those? So a discrete random variables is a variables. Variables is some like you can say like as a what if it is an input. So the variables that you want to model would be inter-arrival times, or if it, maybe for an inventory system, or for a inventory management system, that would be the demand. So the number that is random for those, right? Inter-arrival times is random, right? Sometimes big, sometimes small. Um, the if the value, if the number of possible value of this random number is finite, okay, here keywords, is finite or countable, countable infinite, this will be considered as discrete random variables. So what are the examples? Okay, maybe I can say about if you have ever like throw a dice. Okay, so dice, you know, dice, right? So when you play gambling or Monopoly games, board games, normally it's often involved using dice, right? Dice has 6 faces. So there is face with a 1 dot or 2 dot. I don't know the where does it place. Okay, I'm not often playing like this. 2 dot or 6 dot, right? 6 faces, or maybe this one 4. Difficult to get. So whenever you throw the dice, okay, what are the possibility of a number of a value will appear from the dice drawing? That would be only 6 number, right? Is it 1 face? Face of 1 dot, right? 1, 2, 3, 4, 5, or 6. So the it is random, but you know that the number of possible value is finite, only 6 in this case. Okay. So with that example, that was so-called discrete random variables. Okay, random variables that you know there will be a finite possibility of the appearance of this value. What other are discrete random variables? Throwing a coin, flipping a coin. So if you assume that one side will have value of 1, another is 0. So when you flip this coin, only 2 options, right? Either 0 or 1. This is also discrete random variables. Okay. Therefore, now we know that with discrete random variables, we will have another terminology, so-called probability distributions. Okay. What is probability distributions? So it's basically the probability, the chance of, let's say, if you take the notations as this one, right? Probability of a random variable x, yeah, where if you have or also written as p, capital P, x equals xi, okay, the variable x will be equal to xi. For example, in the case of drawing dice, so the value probability of xi will be either 1 or 2. This is too small. Maybe I try to make it larger. This, okay, can be 1, 2, 3, 4, 5, and 6. Okay. 5 and 6, right? Guys, okay. The probability of 1 will appear would be this one. 1 divided by 6, right? 1/6 of the percent, right? So means that when you are being asked what is the probability of random variable x, the of random variable x will be equal this value 1, and then what about 2? 2 would be the same, 1/6, right? And the same for all of them. 1/6, 1/6, 1/6, 6, and 1/6. Okay. So this is what called the probability of random variables. Okay. And then if you are being asked to write, let's say, states the value, yeah, this one, the collections of this value. So probability of x when of xi when I is equal 1, 2, 3, 4, 5. This will be so-called probability distributions. Okay, and when you probability distributions, when you have the collection pair xi, so if I xi this one 1/6, right, and then 2 is also 1/6. This would be called probability distributions of x. And pxi is so-called probability mass functions of x. Okay, so this is one terminology. Okay. Another examples, okay. We do also have so-called continuous random variable. So what are those, and what is the difference between these continuous random variables with the previous one? So x is so-called continuous random variables if the range of the space, okay, earlier the space that we have, right, is for flipping a coin 1 and 2, so either 0 or 1, right? For drawing dice, so it will be either 1, 2, 3, 4, 5, or 6, right? It is finite. But now, when you talk about continuous random variables, the range value of x will be in a range space or interval or collections of it. So it is a continuous, right? So with that said, you can write the functions, okay, to show that the probability of x, for example, lies between the interval of a, b, would be given. Yeah, so here. So here, this is a, this is b. So the probability of x between this interval will be, yeah, this one, right? Will be this, would be, how do we calculate the area of this denoted area? it will be integral, okay, of this curve, right? So function of x from A to B. Okay. That means that yeah, it's different where compared to discrete event, discrete variables, discrete random variables, because the possible value for this case would be continuous, right? So, for example, what are some things that can be modeled this way? The surface time, right? Despite it could be like, okay, 10 minutes, 15 minutes, 30 minutes, but sometimes it would be in between, right? Maybe 22, 22.5 or something. Machine lifetime, that is also continuous random variables. And then delivery lead time and so on, okay? And unlike the discrete random variables, the probability density functions of this would be set denoted as this one, right? Previously we have p of x. Now we have functions of x, where the fx would be always greater than 0. Okay, and that would be some things that we will review. Why we do need this to review? First of all, because later when you have the the data that you are going to deal with, and then you are trying to simulate, you need to understand if you are going to treat those data as a random variables, whether it would belong to a discrete random variables or continuous random variables. Okay. Okay, take example of this one. There is a data about in lifetime of an inspection device. And then after several data collections, the scientists that inspect this device understood that the lifetimes of this device will be given by X with a continuous random variables. Means that the lifetime will be not a discrete one. Maybe it can be a value in between or range. Okay, and then even so, we do have the probability density functions. Okay, okay, PDF of it, right? So the value of x would be either this one, 1 per 2 exponent minus x per 2, where x is greater than 0, yeah, this one. But if it is x is equal to other than this, so less than 0, it will be equals to 0. Okay. So what we can understood from this? Okay. First of all, let's say x has exponential distribution, which means is 2 years. So yeah, the means of the lifetime of this product is 2 years. However, if you are being asked, what is the probability of this device life will be between 2 and 3 years? We do have it here, right? Between 2 and 3 years. So x will be here and here. What is the value of this? The probability. So you can plug this to this one by calculating what would be the p of x in this range. So this is 2, this is 3. Okay. So it could be calculated by, yeah, this one. Put the limit, lower limit here, upper limit here, and then integral this one. Okay. Of course, I will not display to you how do we calculate this integral. You can even use ChatGPT now to calculate integrals. And then basically you need to plug in the limit value, the upper and lower, the upper and lower limits of this integral value. Okay. Finally, we will have this number. What does this mean? Means that the probability of the device will have still alive between 2 and 3 years would be 14%. Okay. Yeah, that was one of the way we can use the probability density functions. Next would be so-called cumulative distribution functions. Okay. So the cumulative distribution function, or CDF, is written in this one notation, capital F and X. It basically represents the probability that a random variables is less than equals to a certain value. Yeah, this one. Because it's a cumulative. Like when you have the dice experiment earlier, this one, 1, 2, 3, 4, 5, 6, right? The PDF would be 1 per 6, 1 per 6, yeah, 1 divided by 6, 1 divided by 6, 1 divided by 6, 1 divided by 6. Then the cumulative distributions would be this one cumulative is 1 by 6. This one cumulative is 2 by 6. This one 3 by 6, 4 by 6, 5 by 6, 6 by 6, or equals to 1. Yeah. So this is so-called the cumulative distribution function for this one. For a discrete value, it will be like this. But for a continuous, you need to calculate it as an integral from minus infinity to the value of x. Okay, and understood that the fx is non-decreasing function. So if you have a is less than b, then fa is less than f. And this one, limited x to infinity, would be 1. Why? Because this one, you see, the total probability should not be greater than 1. Okay. Next is about the inspection device. So the same one. So if you have probability PDF of this one, and then if you calculate the integrals, okay, so from 0 until x, then you will get this value, right? Okay. Again, I'm not explaining the detail of how we can calculate the integrals. So now the question is how we can understood this. This is the probability that the device is going to last less than 2 years, because we have the x is equals 2 years. 2 years is the guarantee. But is that any probability that the device will be last less than 2 years? Yes, of course. The way you calculate this like this: the p of 0 less than x less than 2. So the value of p0 is f2, right? And then minus this one. So f2 minus f0. So we'll get this one. So what does it mean? It means that the probability that the device would last less than 2 years would be 62.2%. So next means that when we combine with the previous informations, okay, less than 2 years will be 63.2%. But from 2 to 3 years, it reduced, right? Only 14%. Maybe if you prolong the time frame, it also reduces. Okay, but the total cumulative distribution function will be equals to what? To 1, because all the sum of all probability should always equals to 1. Okay. I think yeah, it's quite a lot to digest, right? After this is even more. So I'm thinking about, I will finish here in the expectation value. Okay. Expectation value. So when you have the expected value of x, what does it mean? It actually means like this. Okay, you know the value of xi would be, for example, in the in the in the dice dice drawing. Draw the dice. It will be 1, 2, 3, 4, 5, 6, right? So the total of this one is 1 plus 2, 3, 3 plus 3, 6, 6 plus 4, 10, 10 plus 5, 10, 10 plus 5, 15, 15 plus 6, 21, right? And means that then if you want to expected value of x will appear will be, you need to multiply the total multiplied by 1 per 6 is the probability, right? So those are the expected value that's going to appear in your drawing the dice. If it is continuous, the formula will be changing to this one. And it is also means what? It is also means that the mean, wait. It represents the average outcome if the process is repeated many times, okay? Like for example of the, drawing the dice earlier, the expected outcome will be those number. So those are called E, okay? So later, this also would be showing what? This is what we call as mean, okay? Mean average, okay? And then, so if you have the mean average, you will also have its friends, which is so-called this one, variance. What is variance? Is the deviations from the expected mean, okay? Or standard deviations for here, example here. Okay, so in simulations, the expected value or the mean value and the variance will help us to understand both the central tendency and the variability of the system. So that's why we need this understanding here. Okay, so I guess for today, since it's all about mathematical formulations, I will try to stop it here. So for this module, let's divide it into 2 meetings. Today's meeting will be only 1 hour. Next meeting will be another 1 hour to finish all of this. Okay. Up until here, do you have any questions? So what we are studying about today is that you will enter the use of statistical model to represent what is random variables. Okay. Random variables, we do have 2 types, whether it's a discrete random variables or continuous random variables. And this is one of the way you can use it. And other than that, you also have so-called central tendency of the variables, of the random variables. And then you do have the variations of this. Okay. And later, we will be introduced to several types of random distributions, including exponential distributions. This one is discrete distributions, Bernoulli, binomial, and so on. And we also discuss a little bit about where does these distributions fit in the what kind of process in the simulations. Okay. Okay, up until here, do you have any questions? No? Yeah. If not, let's finish it here. Okay. Yes, Mr. Ken.
None so far, Doc.
Okay, great. So if again, I would like to also remind you again, if you haven't finished doing the quiz, now it's a good time because we are almost cover all the module 1, module 2, module 3, and module 4. Module 4 is half of it, right? So start doing the quiz. If you got perfect score, then great. Then move on studying the module 5. And I will upload the rest of the module 6, 7, 8 here. And then you will have another quiz. Okay. So that would be it. Thank you very much, everyone that joining today's sessions. Appreciate your effort. I just invite you again to let's do another extra effort doing the quiz. Okay. So thank you very much, everyone. Oh, wait, there is a question. Would like to ask, when will be the end of our semester? This is week 8, right? Next week is week 9. So your semester will be end the same with the rest of the students. Means that after week 10, I will give I will check all the gradings. We will have at least 3 quiz or 4 quiz, and then check based on those gradings. So we do not have projects in this class. Okay, I would like to very much to have project, but for online class, normally it will be very difficult to find time to you to work on a project. Okay, as actually simulations is more interesting when you're doing project, but unfortunately, I think with the limitations of time, as well as the understanding your workload as a part-time student, I'm thinking about let me give you the proper understanding about the theory, and then if you are interested to apply it in practice, you can use it as your options to do like a thesis research. Okay, so that would be some things that I can suggest for these courses. Okay, and the course will be end like next week, I guess. Let me check with Dr. Yang about it. Okay, so thank you very much, everyone, for today's sessions. Let's meet again tomorrow. Bye bye.
Bye, Doc. Thank you.